So we are going to start. So we continue our how we just formulated a mathematical way of how we can just have representation of quantum mechanics, whether it's operators, whether it's state function psi. Now and how we can represent whether they are orthonormality conditions, orthogonality conditions, and so on and so forth, and how we can represent psi in terms of expansion coefficients of Cn, whose probability amplitude at the end should come out to be 1. So here we are going to use some properties of vectors and inner products which are basically defined in an abstract space which we normally call Hilbert space. तो उस चीज़ को हम थोड़ा सा सस्पेंड करेंगे फॉर सम टाइम. व्हाट्स इन हिल्बर्ट स्पेस? फिलहाल आप याद रखो हिल्बर्ट स्पेस आर द इन्फिनिट डायमेंशनल वेक्टर स्पेसेस. जो वेक्टर स्पेसेस हैं उनमें जो एलिमेंट्स हैं दे स्पैन a set, and that the elements are the states which will correspond to these states psi, which we can see the operators acting on those states psi which span on that space, abstract space. अब हमारे पास जो we are going to have some properties like that of vectors and inner products. So if we have, for example, our abstract space, if it's collection of vectors denoted by psi, and psi can be combined in terms of psi A and psi B, then you can have this property: psi A plus psi B is equal to psi B plus psi A. Or you can have associated by addition, psi A plus psi B plus psi C is equal to psi A plus psi B plus psi C. So in the same way, we can have, if we have an arbitrary complex number, lambda, such that lambda is arbitrary complex number, then lambda plus mu into psi will be equivalent to lambda psi plus mu psi, and mu times lambda psi is equivalent to mu lambda psi. Or if we have an identity element 1 into psi is equal to psi. So identity element, the product of identity element vis-a-vis psi comes out to be same. Or if you have a null vector 0, then psi of 0 is equal to psi, and 0 of psi is equal to psi. So you know these properties, but we are somehow we know them in terms of numbers, but we are trying to see how we can see them through these vector spaces, which are represented by these states psi and psi A and psi B. अब हमारे पास if you know something called linear independence and linear dependence, which we have time and again. So lambda 1 psi 1 plus lambda 2 psi 2 plus so on and so forth, lambda k psi k. So if it's linearly independent, lambda 1 is equal to lambda 2 is equal to 0. So in an n-dimensional space, n linearly independent vectors psi 1, psi 2, so on and so on, इसी को हम बेसिस भी कहते हैं. the basis vectors which span that set on that thing, on that Hilbert space जो हमारे पास है. अब ये है कि we are coming back to, for example, if this span is set psi, so how can psi be written as 1 to n ai psi I. So ai are the complex vectors. Sorry, complex numbers. So you can say psi, we know already, हमारे पास जो psi है, it's the expansion coefficients of a1 psi 1, a2 psi 1, the components of this psi in terms of these difference will give us they are the components of the psi. अब ये है कि if we represent psi in terms of, as we have represented psi in terms of psi a and psi b, then if psi a is represented as ai psi I, psi b is represented as bi psi I, then psi a plus psi b is equal to bi psi I. So if it's like that, we can have these scalars outside. And similarly, if we have a scalar psi lambda psi a, it can be written as lambda a psi a. You can have this property. Now, हमारे पास how do we define inner product between two these vectors psi a and psi b. This is a thing how we can define, because inner product is very much important, and there psi a psi b is not equal to psi b psi a, but it's the since where psi and psi b are represented by complex numbers, so the property which they are going to satisfy is basically psi a psi b is equal to psi a psi b conjugate, and psi a lambda psi b it's, if you multiply it by scalar, the property is that the scalar will come outside. It's like this, psi a psi b. Or now if you just keep it here the way we had here, psi a psi b is equal to sorry, it is psi a psi b is equal to psi b psi a. Sorry. So if you flip, हम अब इसको flip करेंगे एक ही जगह b, but this will become psi conjugate. In the same way, so the scalar will come outside as a property. But now if the scalar is kept here, one of them will become conjugate. So lambda psi a psi b, अगर हमने scalar को यहाँ लिया, so as a property it will come out conjugate property. It will be psi a psi b. And we can also postulate. We can also postulate. We can also postulate psi a psi b plus psi c is equal to psi a psi b and plus psi a psi c. So we are merely हम enumerate कर रहे हैं different properties of these vector spaces. These elements of vector spaces which are denoted by this psi, and psi can later be substituted as if it's a wave function. How it is going to. So the properties of psi, mathematical properties, but later we can import some physical meaning to them. That they are following certain properties. So if it is like this, and now psi A, psi of psi is basically, so this is the inner product. The NOR, it's also called the NOR. So inner product is always greater than 0, or it's normally 1 or 0, but we can say it's, so if normally this psi of psi is equal to modulus of psi is called the norm of the length of vector. So a vector for which size come. No, it's class. 30 minutes. Can class? Yes. W. No, it's telling this class as this doesn't 20-30 minutes. Who puts in it? Who puts in it? So psi is greater than 0. So if it's like that, then so if two vectors are orthogonal, then they are going to vanish. The inner product will vanish then. The inner product vanishes. As it's not orthogonal, vanishes. And these conditions, psi I, psi j is equal to delta ij. You can say it's orthonormality or orthogonality conditions. So orthogonal means if the components are, if individual vectors may not necessarily be 0, but they are orthogonal, then the inner product will come out to be 0. So individual vectors may or may not be 0. If they are not 0, but the components are orthogonal to each other, still the inner product is 0. Or otherwise, it's equivalent to, for I is equivalent to j, it's equivalent to 1. Now we are going to take what we can take so we are going to take so inner product of arbitrary vectors can be expressed as psi A, psi B. So these are arbitrary vectors. They can be expressed as so it will be sigma I, j, ai star, bj star, psi I, psi j. So if psi and psi b, so psi a is represented by a, psi I, b. So these scalars will come out. So that's it. And if psi is equal to psi j, I is equal to j, this is equal to A if Bj. I is equal to J, so it's further you can have if A is equal to B, so it will be AI square. So modulus of psi of psi, A is equal to B, so it will be equal to sigma of I, P of I square. So for so if psi is a complex valued scalar function, so another exercise you can say if psi is a complex valued scalar functional, then f of a lambda of psi of b plus mu of psi of b c is equal to, so these scalars will come out lambda times f of a psi of b plus mu times f of a psi of c, or f of a psi can be represented as psi of a psi. So 9 point, this defines psi uniquely. So it's also called Rees representation theorem. Now what we are going to, अब हम क्या करेंगे काम, what we are going to do is basically we are going to see how we are going to represent them these things by operators. And operators in vector space, that's it. So operators means, so we define a position operator. We define operators in a vector space. So any operator A is a prescription for which active every vector psi in a space is associated with. So psi prime is equal to A of psi. So an operator acting on psi will be associated with this thing. And there can be special class of operators A which act on psi A plus psi B such that you can have just like we have a scalar property, the operators are also going to act just like हमारे पास scalar addition है. The same way you can have an operator acting on lambda psi, lambda a psi. So operator okay. So operator acting on this psi, operator acting on this psi, so the scalar will come out of it, where lambda is arbitrary complex number. And if they are having this property, such operators are called linear. So linear operators हमारे लिए they are very important in the sense that linearity as a condition becomes restrictive in that sense. If you later see when we just see the commutative property in quantum mechanics, how linearity as a property spans out. So, for linear operator, psi prime is equal to A of psi. In the same way, we are going to have antilinear operators. For antilinear operators, so the operator A times A operating on lambda psi. So the scalar is here. So what will happen? The scalar will just adjust. Scalar will take the value of complex value in case of antilinearity as a condition. So linearity condition is defined. If an operator acts on this, so it is going to satisfy these two conditions. One is the addition, associated with the addition and multiplication. And the scalars will come outside. But in case of antilinear operators, we define it as complex conjugate will come out. And if there are two operators, this is what we are basically interested in, two operators. So we having so for us two canonically conjugate operators or two operators, simultaneous operators, they become हमारे लिए important हो जाते हैं. So two operators or A and B or equal if A psi is equal to B psi, means A acting on psi will give the same thing as B acting on the psi will give the same thing, and such that further A plus B psi, sum of two operators acting on given state psi is A psi plus B psi. And again here, once we say that just like we say AB is equal to BA, it's not necessary that AB should be equivalent to always. Sometimes it can be, but it's not always that AB is equal to. So this means product of two operators will not depend upon if we change the flip the place value of A and B. So in one sense it means operator A is acting on psi, for example AB psi is not equivalent to BA psi. What does it mean? It means first B is acting on psi, then A is acting on B psi. So here in the second case, A is acting on psi and B is acting on A and psi. So this means product of two operators may not necessarily be the product of operators if we flip the sign. So now we are going to come to something called as identity operator. So identity operator means that so it operates on the given state and the state remains unchanged. Psi is equal to I of psi. And or lambda of I is a lambda is a mere number, so it merely multiplies with the constant. So if the I is the operator, it merely multiplies with the constant. So a less trivial example of linear operator can be given by so it can be given by where psi a is a unit vector. Yes, yes. We'll continue. So we can continue. So we have if we define psi a as this thing, then so if we want to define identity operator, another trivial example of a linear operator can be this thing. Here psi a is a unit vector, and for psi prime, you can have P of A is psi. So you can come to something called projection operator. An operator acting on a in state psi, it will get the state back. So it will get the absolute value of the component psi A, psi of psi in that direction. So if there is an exercise which helps us, for example, if there is a P, you have to show that PA is a linear operator. P projection operator, PA, psi A. So in operator which gets the component of the gain state back, psi A in that given direction. So you have to prove this property. So it will follow from this thing. We have a so there is another property called idempotency. You have if you scale a matrix, the matrix will come back. So you have an operation. You just again have an operation, and things will come back to the original state. So P of A square psi. So P of A psi of P of A. So it should be equal to P of A psi. So it will be P of A psi. So, but psi you have denoted as P of A psi. So it will be psi A of A psi. This is psi prime. This psi prime. So it will be equivalent to psi of A and psi of prime is equal to psi of A psi. So you can say it's psi of A psi. So it will be P of A psi. So for an idempotent for a projection operator to be idempotent, we have P of A square is P of A. And particular for the projections on the basis vectors can take this form. P of psi I is equal to psi of I psi is equivalent to psi of E. So we can see if we have P of I, P of J acting on psi should be equivalent to A times P of I psi J is 0. So this means consequently P of I, P of J is equal to pj, pi is equal to, so they are commuting. Projection operators are commuting for I not equivalent to j, but they not be necessary for every thing. So there is linearity condition. The product of two operators may or may not be true zero generally. So in the same way for projection operators, these commuting operators may be zero for this condition and they may not be. So for every psi, psi, sigma I is equal to 1 to n, p of I psi 1 to n, ai psi I is psi, and sigma I is equal to 1 to n equal to 1. So now, so we can have A is characterized by the so operator A can be characterized by the effect of basis vector such that E of psi of j is equivalent to psi I A I j. So the point is हमारे पास ये है कि जो psi है, if an operator acts on this vector space psi, can we write psi I in terms of these two indices I and j? Here A can be a scalar, or it can be where I and j can take value 1, 2, 2, so on and so on. So if psi b can be written as psi psi of A of psi of A can be written as psi of j can be written as, so if we have, you can go from one symbol to one indices to two indices. So you can have, it is j, you can include I also, j and I. So aj psi I, psi I, A I j, or you can get psi I back, you can have AI j AJ, or this entire thing we can see it basically ये हमारा आएगा बराबर, it will come out to be like this, B of I is equal to AIJ AJ. And basically psi of B is equal to BI psi of I. So this means J and J, so it will be BI is equal to this thing. So element here, how can you relate element here with this element via some with these two component symbols. तो हम इस चीज को we are going to represent it in terms of matrices, such that if we have bi के different values, b1, b2, bn, it's called a11, a12, a1n, a21, a22, a2n, an1, an2, so that ann, so a1, a2, so an. So you can always see how can write B1 को how we can write it in terms of A1, B2 in terms of B2. So to each element we can, so it's mediated by this matrix which has two indices. Now you can relate it, any state psi can be, two states can be mediated by this matrix and two symbols I and j, or you can say two components also. Yes, the state psi it's multiplied by something and two components, which can be represented by this matrix. And if we want to write psi in terms of psi A, psi B, psi A, psi B, so it will be AI star BI, A1 star, A2 star, AN star. So it's B1, B2, and Bn. So the inner product of psi A and psi B is basically A1 star, A2 star, AN, B1 star, B2. So you can have each individual element. A1, B1, A2, B2 plus A2, B2 plus A3, B3, so on and so forth. It will be sigma 1, यहाँ से आएगा 1 to n. So the choice of particular basis determines matrices A1, A2, AN, and B1, B2, so on and so forth. So अब यहाँ पर where psi B and psi A and the square matrix. So we can have and square. So we have states psi A, state psi A, psi B. They are mediated by square matrix. This matrix. This is psi. If we want to write this in terms of psi A, psi B, so they are mediated by this square matrix. So you can have the matrix elements represented by the operator A. Represented by operator A. So if you want to write this square matrix in terms of operator A11, A12, so on, 1n, 21, 22, 2n, an1, nn. So these are mediated by the. So the matrix elements of A are represented as Aij, can be represented as psi of A. So the inner product can be psi of Ag. Psi of I, psi of Ag. So it will be psi A, psi I, psi J. I and J are two indices. These I and J can come out to A1, Aij. So we can also have projection operators also. We can mediate these things via projection operators such that P of Ai, which is having two indices, it's psi I, psi A, psi J. So it will be psi A, psi J, psi I, psi A. So it will be Aj star Ai. Now at the end, what we are going to see is that if we can have this we have done in terms of operators and the properties of matrices. How we can write relate two states mediated by this operator matrix. Now, what were from the general properties of matrix? You know that A plus B I of j is equal to ij plus bij. So now, if you want to place A and B as operators, for example, A, B having symbols ij, two indices, you can also write it in terms of as inner product of two operators, psi I, A, B, G. Psi I, sorry, psi I, psi G. Inner product of two things. Such that you can write it as psi I A times sigma k psi k b k g, or you can write it as A psi k b k g. So it will be A k j b k j. Sorry, b k j. So we can write product these two matrices indices. So these two A and B can be operators with indices I and J. They can be individually at the end. If you have this property of inner products, you can write them in terms of product of two these matrices, AKJ and BKJ, J and AKJ and AKI, it will be I and J. K and K may just sum up, so we can have it. So this is the general summary of how we have in this today's class. हमने क्या किया है कि we just summarize the properties of these vectors and their inner products and properties, how we can write them in terms of matrices. And also one of the properties was that of projection operator, where it has similarity that of idempotent matrix. So we'll stop.